So this is my third talk that somehow will use everything that I told you before, but I prepared something to share with Pablo. Is Pablo here? He's not here. Yesterday, remember that he talked about how fantastic art director he is. He never succeeded in putting pictures on the Nature cover, right? So I wanted to show him two of our attempts. And you guess, okay? I wanted him to guess, but he probably not such a good guess. So this was one that we sent to Nature. This was in 1997 after measuring the fractional charge. So just look at it, because later on you have to vote. Okay, so that's one. And that's the second one. You have to look at it a bit more, because it's a bit vague. But can you see the details that we sent after we published this talk? Okay? Can you see there? There is a kappa over 2, and there is 5 halves, and there is a picture at the top that runs around. Okay, so which one was accepted, rejected, both accepted? Because nobody looks at the cover, right? Everybody looks at the internet and look at papers. Nobody knows the cover. You have any guess? What's your guess? First one. Okay. Any more? Okay, you are right. Okay. So this was the only one out of many tries that was accepted. Okay. Anyhow, so let me move on, okay? So the motivation that we had to go ahead and measure thermal transport that we never measured before, this is something we started like 3 years ago, was because of the failure that I told you yesterday about interference. Because interference is everything. If you see interference, you see braiding statistics, you see everything. Okay, so you have to go around it and find out the nature of the state by some other means. And what we do usually, we just measure, at least my group measure conductance. Okay. So thermal conductance, as I learned in the late 90s, I would say, from Charlie, and later on by collaborators in our department, has a power that conductance does not have, because it doesn't care if you have a charge or you don't have a charge, and it does care if you are a Majorana. Okay, so it can distinguish also. It won't tell you really the statistics of the anyons, but it will distinguish between abelian and non-abelian. So why not? Let's give it a shot. Okay, so the thermal conductance, I just will respell what I just said, is it really gives you a topological number. You see the number of kappa 0 that you will see in a second is an amazing number, okay? Only universal units are there. And it determines from the edge what's going on in the bulk. And this is from the bulk edge correspondence that we heard before. Okay, what it does, it gives you a number, the central charge number, that's the way it's called, and it gives you the net number of neutral modes. Net means downstream minus upstream. Okay? But this is also under some condition, okay? And the condition is that it needs that all these modes will be thermally equilibrated. Okay? If they don't, one carries energy, the other one is totally empty, then you don't get the right number. And that's the difficulty of this experiment. But then, many a times, I showed yesterday, we have this edge reconstruction. New modes appear in the system that we cannot control, but they tend to localize. They tend to gap each other. And if you go to long enough distances where the modes are equilibrating, this edge reconstructed non-topological modes will basically be empty. Everything will go back. Okay. And then that's what I said before. It may prove if you can go to see a Majorana. So the 5-half state is this state that, thank you, Steve, for this fantastic talk that you gave that I never heard before in this form, okay? That let's shoot for this 5-half state. Okay. So just 2 slides, because I was not sure what Steve is going to say. So you have this superconductivity, condensation of composite fermion at half filling, okay? And then if you have this Fermi liquid, what can you do with it? It can be a metal, it can be a superconductor, it can be some exotic state. But since Rxx equals 0, let's just think it is a superconductor. And since everything is polarized, at least in half, 2.5, there was a bit of an argument, but we think it's all polarized, then it is a p-wave superconductor. We don't have singlets, we have triplets only. Okay, so this zero energy, this is the last transparency that talks about this business about the 5-half, is that as you move just a little bit from B equal half, you induce quasi-particles, you induce vortices, because you have now B effective greater than 0, okay? And then you create this Majorana, and I don't think Steve mentioned the number E/4 of the charge that comes around, and I'll show you. This Laughlin argument gives you the E/4 very quickly, okay? Etc., etc., and this is the degeneracy. Here I don't count pairs, I count only vortices, okay? So it's not number of pairs, and that's what you see again and again here. Okay, so again, the Moore-Reed Paffian state, okay, which you will see does not exist in the 5-halves that we measured. Anyhow, this was the very original one, is exactly this half flux quantum over 2, and there is an E/4 particle going also stuck inside here, okay? At the same thing, it goes also a bosonic mode around the edge, okay? And the Majorana is supposed to have a half central charge. And when you really have a good system, okay, MBE system, which I talked about in the first talk, then you can get these zeros, okay, in the what I call a first excited Landau level, okay, where the first two spins are one Landau level. And then you see states, and if you go to people that are doing at very low temperature, they shine light on the system, you see a bunch of many more states here, okay? But as you will tell you later, we are not allowed to shine any light on the system in this measurement. Okay, you see the mobility is pretty high, but the mobility is not a criteria to get 5-halves. Sometimes you get much better, let's call it plateau system with a mobility which is half of this. And sometimes you go even to 35 and you see 0 5-half state. Okay, so this is a mysterious thing. It has to do with the details of disorder, which we don't understand. Okay, so this is, first of all, this is the charge. I'm going to tell you what we know, basically, about the system. Expect a charge. Remember this Laughlin argument, we saw it already a few times. And this time, we put inside adiabatically, we weave inside half flux quanta, and then I have this electromotive force, okay, and I have a charge density going out because it's Rxx equals 0, okay, and then we integrate again to get the charge because of this, and we get exactly the E/4. So the thing is that you will see in a couple of minutes, a few minutes from now, that many orders of these 5-halves, all of them predict E/4. So if you measure E/4, okay, it's great, it's good, but you still have many other possibilities. That must not be non-abelian. Okay, and it's pretty ugly measurement. We improve over the time. I want to show you a little bit when measurements are not so beautiful when you measure the charge, but here is the charge measured some years ago of the E/4 in two different conditions. Here is starting from Finning factor 3 and depleted into 5-halves, and this is starting from the 5-half. Extremely noisy. The system is not easy to work with because of the special design, as I'll show you later, of the donor system. Carriers tend to move around in the bulk, and you have tremendous amount of noise, and it's very difficult to measure noise and get the charge right. Okay, so E/4 was proven at the time. And then the other thing is neutral mode. Remember we talked about neutral mode, and then we measured also neutral mode in 5-halves. At the same time we measured, if you remember the measurement before, we excite, or the first talk, we excite neutral mode at this place here. This is a hotspot. And whatever we measure with 2/3, another thing, we measure also here. So this carries an upstream neutral mode. Okay. So what we know, there is a charge E/4 before we start anything. This is known all the way, let's say, years back. There's charge E/4, they're in upstream neutral mode, and likely spin polarized. Okay? So if this is the case, let's spend a bit of time to look on the major prediction for the order of the 5-halves. Okay? So there is this abelian and non-abelian, and what I'm plotting here, all of them are 2+, okay? So these fat double lines here are just integer, okay? And the kappa of this integer, I'll define kappa in just a minute or so, is 1, okay? And then there is this little thin line with the E/4 that comes around. So this is 2.5. This is the half, okay? And then this wiggle line is just a neutral mode, okay? So it's a bosonic neutral mode that carries also thermal conductors of unity. And then there is a Majorana that is dotted line, that you heard before that carries half of a quanta of thermal conductance, okay? So you see these are billions, so now there are all these names, so it's a bit small, I'm sorry, okay? And this is the non-abelian one, this is the Paphian. And the reason I had put it in red, because this was sort of like the first predicted, and this is the one that is believed by most theorists, and I'll come to it at the end, to be the real ground state of the Paphian, okay? And there are other ones, and you can see all of them differ from each other by the kappa. Okay? All of them has the E/4, all of them has, the question is, for example, we measure upstream neutral mode. Okay? So there is energy going upstream. But you see there are, for example, the Paphian doesn't have anything going upstream. This is all downstream. Nothing goes upstream. Okay, so if our measurement is correct and it's not some reconstruction that is very funny, forget about the Paphian. It's not there. Okay? But the anti-Paphian goes back, okay, and this goes back. All of them that go something back, even the abelian one, there are things that go back. So we can scratch out this particular one, and this one, and this one, and this one, okay? And we have a smaller number of orders that we have to deal with at the end in the interpretation. I'll come back to this table at the end. Okay, so now I'm going now to thermal transport, okay? So let's go back in history to this very, very fantastic paper of Pendry, okay? This is the paper that he wrote, and he basically, half of the paper, he waves his hands, and he talked about thermal conductance of a channel. He calls it a channel. We know it now, it's a ballistic channel, okay? And he starts from he starts from really information, and he goes all the way down and arrives at thermal energy, all with approximation, etc. At the end, he says that every single one-dimensional channel, he calls it, has a maximum ability to carry heat, okay? And this maximum ability, this is what the thermal conductance is kappa 0 times temperature, okay? And the kappa is defined, or this thermal conductance is defined, the derivative of heat, of energy versus time, which is watts. It's power, moving power. Okay, so this, look at this number. Of course, this number was not waving hand by rigorous calculation, and I think that, I forget if Charlie derived it on the board or so, but it's just simple integration. But look at this number. It's just a beautiful universal number. Okay, it's a pi and Boltzmann and Planck, but no charge. You see, there's no charge there. So this is a guess right away that, well, what happens now in fractional charge? Does it carry the same thing? Okay, there's no charge here at all. Okay, it can be neutral, but we have to still talk about the fractional charge. So this number is kind of, 10 to the minus 12, and this is the formula. And now if you want to see the heat carried, okay, when you have a difference in temperature, and this is high temperature and this is low temperature. By the way, all this is linear regime. So if this difference is huge, then there are higher orders, but we talk only about this. All our temperatures are very small, okay? And this is the formula that really we have to work with all the time. So it's a very simple formula with this magic number. Okay, and then I just want to remind you the Wiedemann-Fritz law that gives you the difference, the ratio between them, okay? And this ratio have now the charge, because the conductance has charge, but we are going to break it. Because we are going now to replace E by E/3, and this equation won't be correct anymore. Besides, this is really not a law. This is kind of an observation of many, many materials, etc. Okay, so this is a conjecture that we are going to break down. Okay, so let's go now to a bit of history. Okay, so it was measured already a long time ago in Caltech, okay, by measuring now phonons, okay, because we say no charge, right? So this was a bunch of like 16 modes of phonons that had been calculated. This was a very pioneering, fantastic paper. I was not aware of it until a few years ago. And then it was measured also by photons, okay? And then this work motivated our work. It was measured by the group of Frédéric Pierre in a few years back. And he measured again also the quantum Hall effect, but only the integer regime. And he proved that Wiedemann-Fritz law call it, works fine. So the work they did, we basically, I would dare to say that we pretty much copied it and improved it somehow. The idea came from him. Okay, so first there is this Pendry general theory. He just deals with some bosons. But then in 1997, Charlie and Kane and Fisher wrote a paper that say this should hold also for fractional charge. Okay? Okay, so this is also a very important paper. I remember Charlie told me many times in the past, why don't you try to do this experiment, okay? This was 1997, and it took us another, 20 years to do the experiment, okay? So interaction should not affect this kappa 0, okay? Okay, so we are going now, so all these theories about one-dimensional modes, and the quantum Hall effect and friction quantum Hall effect is a fantastic medium for for one-dimensional modes. Okay. So for example, if you take particle like 1/3, I go back to Ken and Fisher, okay? Okay. And then I go and I want to show you also this. So for example, this one, and I'll go back to it a few times, I'll come back again and again, since this is supposed to be a tutorial talk. So this one is just kappa 0 because it's a single mode. So kappa, this is the maximum number, okay? But if it's totally ballistic, you should get kappa 0. And 2/3, we have now two counter-propagating modes. And I told you before that the kappa is measured the net number of modes, downstream minus upstream. So the 2/3 should be 0, okay? So if you take, just to give you an impression, if you take a contact and you heat it up and you sit in 2/3, and forget about phonons, it will blow up. Temperature will go up and up and up and up, and it will melt. It will melt. Well, phonons are there, so it won't happen, of course, but it's a bit amazing, right? Okay, so here is sort of like from Charlie's paper with a bit of an extension, and I'll talk about all these four. So kappa, this is 1/3 kappa 0, one composite fermion mode. That's exactly what Steve talked now. This is two composite fermion mode. This one is 1 plus 1. It's supposed to be 1 minus 1, okay, in the 2/3. There's a neutron going up. And this one is going to be 3/5, which I'll come back to it, which is 1 and minus 2. So this one, it will be minus kappa 0, which is kind of amazing that, the current goes in one direction and net heat goes in the opposite direction, right? It's difficult, but I'll give you intuition for it in a bit. Okay, so first of all, the way that we excite neutron modes, okay, I told you before, yesterday, that we can do it in a QPC, or we can do it in the backside of the contact. Here it will be from the contact itself. The contact is very small. There is no back and front. You will see in a minute. But there is half of the power is dissipated at the contact, okay? Half of it carries by the downstream mode, half of it dissipated in the contact. And this one is a nice lamp to heat up and have it. And I showed you also these bubbles, remember, in the first lecture that I gave. Okay, so now I'm going to the experiment itself, okay? And I'm going to just go step by step how we build it up. Okay. By the way, somebody should tell me 10 minutes before. I don't have a watch on me, so I don't have. Okay, so you take a reservoir, you heat it up, okay? And then you let current go out in, let's say, one dimension. This goes to be edge mode to some cold reservoir. Okay? And then there is also, so there is heat moving this way, which I'll call it JE, and there is heat through phonon, J phonon. And you can find a very, very detailed paper that talks about heat transfer from electrons to phonons, okay? And you see the power is 2 to the 5th, and this is the beta, the prefactor is only for our particular ohmic contact, you will see, our particular reservoir, okay? And you see that at very low temperature, since this will be T square, and this will be T5, so this one will not be relevant if you are working at low enough temperature. Say, in these numbers, if you are anywhere below 40 millikelvins or so, heat it up to less than this, you can forget about phonons. But if we are above, we have to address them, and then you will see how do we address them. Okay, so now how do we place this lamp, this candle, by heating it up? So we just run current. But to run current is not enough if you run current through a floating, this is a floating contact, this is a floating contact, a contact connected to the 2D gas, but it's floating. It's not connected to the world, only via edge states, okay? There's no metal taking it out and cooling it or whatever. So if you run current in, then if there is just, if there's no way that you can reflect back or anything like this, if, you come in and you come back outside the contact, then the current will come in, the current will come out, nothing will happen. So you have to split the current, okay? So the current comes in, and then it equilibrates here, okay? There is some V in, and this becomes some half V in this particular two-arm device. Half of the current will come here, and half of the current will come out. This is cold current coming from the back, okay? So you will see that the current split into half and half, but this plus this is equal this. If I just write it down very simply, you get here that the dissipated power, the in minus the out, is equal P over 2. The input power over 2. If you have more than this, then the formula changes a little bit. I'll show you how. Okay, so we hit this floating contact by running current, and the current that comes out is being split. Okay, in this case, 2. Okay, but our device is a 4-arm device. Okay, we can count from here, and then reflected here, coming out here, and coming out here. Of course, each of these arms have 2 modes, downstream and upstream. Downstream, I'm talking about the usual one, even filling factor 1. One comes from hot to cold, and on the other side of the edge, from cold back to hot. And the power dissipation is 1. If it will be 2 arms, it will be 1 minus half, which is half. If it's 4, the dissipated power will be 1 minus 1 over 4, 3/4. Okay, so 3/4 of the current. So it depends how many arms are open or closed. Okay, so now we measure, after we do all this fabrication and make sure that all the details, which I'll show you in a minute, are checked, okay, we measure only 2 temperatures. That's all. Okay, because we know the power dissipation. We know to calculate it. So we measure T0, what's the temperature of my electron at the ground, okay, with the flux that comes back from ground, what's the temperature before we heat it up, because we have to do T minus T0, and the temperature of the reservoir, Tm. Okay, these are the only 2 we measure, and then we plug. That's all. So it looks like nothing. You measure 2 temperature, and that's all. Yes, but it's not so easy. Okay. So now, that's what I said. Small t, the phonons are not relevant. At high t, I subtract out the contribution of the phonons, which I'll show you now. Okay, so first, how do we measure the temperature of the electron? It's not easy at all. When people say temperature and write temperature there, they write the temperature of the fridge. But if you want to write the temperature of the electrons, that's a different story, because they can be totally detached from the fridge. Electron-phonon interaction, at least in gallium arsenide, 2D gas, is very, very weak. Okay? So if we want to go, for example, you have to, there are all kind of tricks and filters and things like this, but suppose you want to go down to sub 10 millikelvin, it can take days. Okay? It can take days, depends, how you're connected to ground, etc. So eventually, when things settle down, how do you measure? If you remember the 2/3, why do I show 2/3 and not 1, for example? Because you remember the 2/3, I showed you the 2/3, and was a plateau of 1/3 and going down. This was yesterday, if you listened, okay? So measuring on a plateau is fantastic because the transmission is constant. We measure noise as a function of I, and we want the T1 minus T to be constant. If it's not constant, what do we use? So on a plateau, the transmission is half all the time. So in 1/3 is beautiful, and we know that the answer is 2/3. We know it from the past. So we measure, you see, this is the very sharp. At 0 temperature, it's really a point at the back. And we can measure here temperature and see this is a beautiful, The result is good to plus minus about half a millikelvin, which is not bad. Okay, so we always measure a device. We try to find the 2/3 very quickly. If we know, then we try to find 5/3 or something like this, and sometimes 1. But 1, the transmission of 1 in QPCs are not so linear, depending on the device. So T0 is very important to know. And then how do we measure now Tm? Okay, so Tm, how do you measure the temperature of the contact that sits in the center and you are not allowed to touch, right? It's just floating there. So we measure basically the current fluctuations, okay, going all the way to the end of the contact, or all the way to the ground somewhere far away, okay? And one can say, well, I'm sure that your edge mode maybe conserve the current, but it doesn't conserve necessarily the energy. So this is a tricky point, okay? So if now the edge mode starts hot, and on its way that can be hundreds of microns, it loses energy by capacitive cooling, by phonons that eventually take something out. So you come to the other side much cooler. So what? You measure the temperature over there here. But no, the idea is that you have charge conservation or current conservation, and you measure at 0 frequency in all respects, like a few hundred kilohertz. So the shot noise at few hundred kilohertz that starts at the ohmic contact, not shot noise, I'm sorry, thermal noise, is preserved independent of the distance. If you don't lose current to the bulk, if electrons don't go anywhere. So that's an amazing fact that helps us to measure far away the thermal noise and know the temperature of the floating contact. Okay? And then we measure this G is not a GQ, it's a modified G because it's a floating contact. There is a formula I can show you. If somebody is interested, I can show you what G to put inside. Okay, so basically now, so we measure TM. For example, this is the measured noise, and from there we know how to measure the temperature as the current increases. Okay, so we can measure the noise at each point, and this is the temperature. This is TM that I have to plug later on into the equation. Okay, so now I want to tell you how do I do this subtraction. First of all, this is the dissipated power that you've seen before. And phonon dissipation depends only on, it doesn't matter how many arms I open, right? The dissipation of the phonon from the contact depends only on the temperature of the contact, okay? If it's hot, it will be T to the fifth of this. If it's cold, same thing. So if I somehow work at high temperature, I don't have enough signal, I have to go to very high temperature, okay? Then I want to subtract the phonon contribution or somehow taking into consideration. So the way that we subtract it, it looks messy, okay? So first take a look. Suppose now I wrote it, the dissipated power for Ni open channels. Let's say 4, okay? So I run 4, and I have now, this is 4, and this is I don't know this number. All the stuff I have to calculate, okay? So this power is half Ni kappa this minus this plus phonon contribution at this Tm. Now I go from 4 to 3, okay? But now I change the current and everything that I get the same temperature, okay? Now I subtract these two, so the difference in power dissipation and the Tm and the phonon are subtracted out. So if I measure it 4 and I measure it 3 and I subtract out the same temperatures all the time, then I see only the contribution independent of the phonon. Is this kind of a messy a little bit? Okay, but let's go, assuming to understand it. So phonon are subtracted out. Okay, so now this is an example. So I have this is a different number of arms. Okay, this is the theoretical picture, sort of. And then every time I cut it off by some Tm, specific Tm, and this difference is this delta P that I subtracted out. And I use this. And this is the actual measurement, okay? Delta P, I change now the power rather than showing you this proportional to I square here. And I measure here, and I do this, and this is the difference that I get, and I take into consideration. This is 4 minus 2. And many times I show you 4 minus 2, and these are two channels, let's say, filling factor 1, and I divide by 2, and I get the thermal conductance. So here's an example. Eventually, I normalized it here, and I get a slope, and this slope is slope times kappa 0. Okay? So this is the actual result, which I'll see later. It was measured in 1/3. Okay, so how do I now cut down the number of arms from 4 to 3 to 2? I just use some gates. Okay, so this is 1, 2, 3, 4. This is an SEM picture of this, and this is a typical OMI contact floating in the center. And the area of this contact is about 30 or 40 or 50 microns, okay, square. And then when I want to go from 4, right, because I have here 1, 2, 3, 4. These are the cold current that comes back from ground. Okay. Then if I want to take it, I close it with a QPC or continuous gate very nearby, and this current is, and edge cannot move out, it just returns back, and I have now 3. And that's the way I move from 3 to 3 to 2. Of course, I cannot go to 1 because I have to split the current. Okay, 2 is the minimum. And this is the actual device. Just show you an example that sometimes if I work with filling factor 2, and I want only to have one edge going out, okay, and the other one comes back, I can just take the QPC and make, you see, the number of channel, the number of arm is 2. Filling factor 2, it means that I have 2 edges. It's not a very good choice of colors. This is green. And then the QPC is 1. So one goes in, and another one comes, reflects back. Okay, but you got the idea. And the device itself, away from the heart of the device, is more complicated because it has, you see, all this mess, many contacts here, and this is sort of another 1 arm, 2, 3, 4, and all these little regions here are added parts to calibrate the amplifier. There is here cold amplifiers, which I talked about them in the first day. And the gain of this amplifier is super important because it determines for me the 4 kTg. So I have to do this calibration. You saw this 2/3. You see this V shape. This is done with this calibration, 2 amplifiers here. So this fabrication of this device is not simple, okay? And the yield is not very high, so anyhow. So now I just want to tell you point of consideration, which means difficulties in other words, okay? So electrons, first of all, have to equilibrate in a small reservoir to 2 em. It's not supposed to be the temperature. We're supposed to be able to define a temperature for the electron. Because if you don't define a temperature of the electron, if it's tiny, tiny, too small, and you don't have enough material inside, okay, then you can get also, okay, shot noise. So the outgoing charge channel carry only Johnson-Nyquist noise and not shot noise, because otherwise the noise you measure will be not reflecting the actual temperature of the contact, okay? And then the other problem that I'll come back when I talk about the 5/2, that the bulk should be insulating, thermally, okay? Not electrically, but thermally. You don't want anything to go through the bulk, only through the edges, okay? Okay. And then the length of the RM is limited. So in this particular experiment, I told you we work with 150 micron long, and suppose the equilibration length is 300. So we have a problem. And you will see it in 2/3 that, you know, if you go very, very far away, you make it 0.5 millimeter or so, you start losing something that leaks to the bulk also. So you are limited. In quantum Hall effect, you just measure, you know, a micron or 2 micron, you see the conductance. Here you have to go far away, long away, and then you may suffer from all kind of stuff that happens on its way. You know, if anything that will take you from this edge of the RM to the other, you're in trouble. Heat or current. And then all the RMs have to be very identical. The plateau of each RM has to be overlap with the other plateau, okay? And gain has to be determined, etc. Contact resistance has to be clear, blah, blah, blah. If somebody wants to start working on this, be my guest. I'd love to talk to you because I would like people to make such measurement. If I do it alone, it's worth nothing, right? A group does something, it's worth nothing until nobody else shows the same results. Okay, so I'm going to talk about this, okay? So the reason that I don't jump right away to 5/2 and finish the talk in 5 minutes, because I have to know first that I know what I'm doing, okay? Because these guys from here up are predicted. We know what is the answer, but here we don't know the answer, okay? Of course, I know the 7/3, but I don't know the answer of this red little thing here. So I have to teach myself, and this appeared in 2 different papers. This was one paper, and this was the other paper. Okay, so first, just to give an example again, I'll go very quickly through it. Okay, so filling factor 2, and again, you measure it, you know, you measure the same measurement at 2 arms, 3 arms, 4 arms, okay, right? Then you do this subtraction, okay? And the same story comes about, okay? And then I want, you know, so you do it now, you can have these 2 modes per arm, 4 arms, 4 modes. And then you can have 4 minus 7, 4 minus 6, 4 minus 2. You can have all these subtractions, right? You can do all these subtractions to subtract the phonons, because when we used this, the temperature was high. The T0 was 30 millikelvin, and we went up to about 60 or so. So phonons are important, okay? So when you do this subtraction, you see all these very nice lines here. And and then you plot the slopes of each of them, and you see that the slope goes up, and the slope per channel is very close to 1. We never get 1. There is always an error bar. Never 1. If you get 1, then we are cheating, okay? So I write 1, but the number is not 1. But I don't think we can get anything better than if you get 0.95 to 105. I'm very happy. Okay, so this is filling factor 2, and I'm going right away rather than show you all the other integers, because, you know, we have to fit. It's 1/3. This is Charlie's prediction. 1/3 should have also a single kappa 0. Okay, and what I want to show you here, the temperature here was already lower. You see it was 10 millikelvin. And then I'm going to show you that, you know, I did not subtract. If I don't subtract, temperature is low, and I look on the whole thing, okay? Delta P, I don't do 4 minus 2, etc. I have here 4, and I have 2. And I didn't subtract it. If I subtract it, of course, it would be very nice too. But you see here, no phonon contribution, because if you have phonon contribution, this has to be also T to the 5th. It will curve up. And I'm plotting here 4kT squared. So this is 4, because it's 4 arms, and this is 2. Okay? So the 4 and the 2 agrees very, very well. Okay? So if you now take and subtract it, you do delta N2, 4 minus 2 divided by 2, which is this, 1 over 2, and this is the difference, you get 1, plus minus 0.045. Okay, so 1/3, and then we measure at 2/5 and 4/3, all of them, it agrees. So fractional charge, fractional states have the same. particle-like fractional state behaves similarly to electron states. Okay, so now I want to go to Hall states, which are Hall conjugate states. Okay, so here it becomes more tricky. And it becomes tricky because we have counter-propagating modes. Okay, so there is a mode going this way and go this way, and now you have to equilibrate between them. So it's not simple. Okay, so we have now to show, indeed, that we get these numbers. Remember the numbers I showed you before. 4, 7 I didn't show you, but this has, as a matter of fact, 3 upstream mode and 1 downstream mode. So you have 2 modes net going up. Okay, this is the one. Okay, so first I want to give you a feel why the thermal conductance is 0 at 2/3. Okay, so let's think about it. So you take 2/3, and I just look on one edge, okay? And here, this is the chirality, this way. So charge 2/3 goes downstream from here to here, and this is, I put here current, so this is a hot contact, and these 2 contacts are cold. These are the ground, okay? This is Tm, and this is T0. And then, okay, now don't forget, I have this hot spot, and I have now a neutral mode going this way. Okay? So now I have a question. Suppose I have nothing else happen. What would be the thermal conductance of the contact, of this edge? I'm not showing, forget about the other one that comes from ground. What would be the thermal conductance that I'm measuring under this condition? How many modes are leaving the contact? Come on, how many modes? You know how to count? 1, 2? 2 modes leave the contact? So what's the thermal conductance? What's kappa? 2. 2, right? 2 modes leave, thermal conductance, 2 kappa 0. However, this is a mode going this way, so here's the neutral mode going this way, right? This is the way. And then the cold downstream mode goes this way, okay? So now you see that you have always the coming pair. These are the counter-propagating modes, okay, in 2/3, okay? And now what happens is that if this is long enough, okay, then you have energy coming from here, equilibrating and coming back up. And the same thing happens on the other side. So if this is very, very, very long, all the energy that will go down will go back up, eventually, depending on distance. And the reason it depends on distance, because this is sort of like a diffusive thing, because the 2 modes, one is hot, one is cold. Think about 2 pipes. One pipe is hot water, one pipe is cold water, and they have to who wins? The cold one or the hot one? Well, they have to equilibrate and come to an agreement somehow, and whereas the heat eventually, if it's infinite distant, all the heat will be carried back. Okay? So this, in a way, the 2/3 is kind of different from the rest of them, because equilibration takes only, I'll show you a picture in a second, in a very, very long distance. So in a way, this particular one is you don't measure here thermal conductance, but you measure thermal conductivity. It's like a resistor. You take a resistor, you measure not resistance, but specific resistance, and as you increase, rho L over A, right? L is bigger and bigger, the resistance goes to infinity. So this is 2/3 when they are separated. Now I interact them, and they don't have the same colors. It takes very long distance because the lengths and the equilibration lengths are on the same order, tenths of microns or so. So this has to be maybe 1 millimeter or 2 millimeter, okay, to start the full equilibration. Okay, that's what I wrote down here. It's a diffusive process, okay. And then I show you here an example, okay, that was calculated by Yuval Oreg and Dima Feldman and Adi Stern, okay. So you start with, let's say, this is sort of like T equal to T0, just as an example. And I have here lengths 10 times the equilibration length. Just pick a case, okay? So downstream mode goes down, the temperature cools down, and the cold one comes up, and they don't meet, okay? If they want them to meet, take this number 10, put it at 100, and then these 2 lines will go on top of each other. There will be full equilibration between them. Because eventually, this has to be hot, and the other side has to be eventually cold, right? These are the 2 endpoints. And the same thing happened in the other direction, this direction up here. And now you have 2 modes, okay, these 2 modes again. Okay, so all of them are repeat. It's one on top of the other. It's difficult to see. And the kappa depends as 2 over 1 plus L over psi. Okay, so it's length depending, diffusive, and it's thermal conductivity rather than conductance. And that's what we said. Remember, if the distance is very, very short, L is very, very small, there is no equilibration. If there's no equilibration, then you have two modes coming out. Nothing comes back in because they don't equilibrate, and it's 2. So you really start at a very short distance for kappa equal 2, which we are trying to measure. We didn't measure it yet because the difficulty when you go to very short distance, then you have all this edge reconstruction. And suddenly multiple modes appear in the system. So it's not simple. Okay. Okay, now, so let's see the measurement themselves. Let's move on of 2 over 3. So now I don't want to show you noise and subtraction and all this thing. I'm showing you right away the result that we get that the slope is not 0, but it's 0.33 kappa 0. Okay? So when you do this is at 10 millikelvin or so, and then but if you look at it and think about the two sides of the arm are equal. Okay? 2 here and 2 here. So if you divide it by 2, really each side of the arm is half of this 0.33. Well, it's not so bad. It's 0.16 or whatever. It's not bad. 0, we have to get probably from a much, much longer distance. But I want to show you if you warm it up, equilibration is faster. Okay? And you go from 0.33, you go down to 0.25 or something like this. So it's in the right direction. You expect now if I could cool it even more, it probably will go up. And that's what I'm going to come back to it in the 5-half results. Okay? When you cool down, equilibration length is longer, and then you don't equilibrate as well as you would like it to be. Okay, so here, if you just calculate a little bit, you get for this base temperature, this is the average temperature because the minimum and the maximum, okay, somewhere in the middle. So this was 30 micron, and then when you warm it up, the equilibration length becomes 20 micron, if you trust this formula that I gave you before, which is simple Newton cooling formula. Okay. So now 3/5, I'm not going to elaborate. It just cools much faster, etc. Let me just go right away to the final results. Okay. So what you see here is that I'm reminding you that this is 1 and 1, and we got something that is you see here the number 0.33 or something like this, rather than 0. It's supposed to be 0. Okay. And then you go to 3/5. All the equilibration take place very quickly because you have 2 versus 1. So always the cold one win. I cannot see the sign minus. In my experiment, I cannot see the minus sign. I see only what goes out in the 2 sides of the arms. And basically, on the left side of the arm, you have most of the contribution of the heat, rather than the right side of the arm. The upstream gain more, but I measure the whole thing together. Okay? And you see here the 3/5. You see this very, very nice line. It's about 1. Allow me to call it -1. Okay, -1. And this is 2, -2. So we know already how to measure counter-propagating modes, quite complicated, all bosonic. Okay, so it's not no Majorana, no stuff like this, but you basically 3/5 and counter-propagating neutral modes, or 4/7, etc. So it works. So I think this was really the first piece of work that we spent initially to teach ourselves how to make this measurement and assure that this is right. So what I'm saying here, that fractional, interacting 1D mode, and neutral mode, all of them have kappa 0. Okay, that's what I'm trying to say. This guy, 1/3, E, electron, neutral, all of them carry the same load. Okay, so now I'm going now to go to 5/2. 10 minutes? Thanks, I'm fine. Okay, so the difficulties we had initially when we start working with 5/2, if you remember, okay, I'll show you it again, that the donor is sitting in like a superlattice, sitting in a little donor you put in a gallium arsenide, and the electrons spill out to the aluminum gallium arsenide, and they can move around with very, very low mobility. So when you do conductance, the mobility of the electron is, I don't know, 10, 20, 30 million, and the mobility of this little electron sitting there in parallel are, I don't know, 10, 20, 100, they sit in a lousy place, etc. Okay, so they barely move. Okay? And you don't see it. It's parallel, but you don't see it because the conductance is so poor. The other problem that we have is we just couldn't make a good contact because the 5/2 is buried very deep inside, and the reservoir didn't make good contact. It's just for the experimentalist. Okay? And then the instabilities of the quantum point contact were pretty messy all the time. Okay? So just to remind you, this is on both sides. This is I showed you one well, and this is a bunch of wells. So the 5/2 state is the reason we do it to get the 5/2 states. Okay? So until now, everybody that grows this 5/2, Loren Pfeiffer, and Werner Wettscheiger, and Michael Manfra, and Vladimir Umansky. Those are the 4 people really that grow this material. Vladimir is in our department. Okay, use this trick invented by Laughlin to get these very nice 5/2, okay, because we screen very well the donors. Okay, yet when you do it and you get very, I just show an example with no light, 29 million mobility, which is sort of like 200 micron plus mean free pass. You get all this bunch of states, okay, even at reasonable temperature. Okay, so these are these 2 superlattices on both sides. So you have parallel conductance, but negligible. Okay, but you have bulk thermal conductors. So when we start using it and we have this nice state, we get huge thermal conductance numbers. We understood very quickly that we have something going through the bulk. Okay. Yet, if you subtract this 4 minus 2 and 4 minus 3, we subtracted out the bulks somehow, and we did get, well, with a large error, etc., similar number that we get here in the result, which I'll show you. But yet you cannot believe it because you have this huge parallel thermal conductor. So we have to go ahead and build different devices. So what we did here, we didn't do this super lattice doping. That's the jargon. Okay? But we really did here delta doping. Silicon in aluminum gallium arsenide, like ubiquitous 2D gas. And then things are frozen at 100 Kelvin or so. No parallel thermal conductors, but it's very difficult to get these very nice 5/2 because this order is much higher. Okay, so I'm showing gamma 2. It means that we overdope. We overdope a lot. When we overdope a lot, the electron that goes away, and what remains, okay, somehow there's many electrons that freeze, but in the freezing process, they tend somehow to kind of smooth out the potential by creating some correlation. Okay. But I have to admit that every paper that you read with this beautiful many states and 0, they shine light. We never shine light. You shine light, you get free carriers all over the place. Forget about this measurement. You don't shine light. So this 20 million that we report on, 0 total darkness, which I don't think anybody does. Okay? So we don't have any parallel conductance because it's DX centers, what I mentioned to you before. There is no bulk thermal conductance. The stability of the gate is good because we replace QPC with a continuous gate, so we have to deplete down rather than close a gap. So instead of putting minus VG equal 10 volts, minus 10 volts to close it, we put minus 1 volt and we deplete down. Okay? And then we put Hafnia under the surface. So there are many little things we did, improve the OMI contact. All these things that you see here took about a year. Okay? It's trial and error, and the experiment is not easy. Okay, so we got reasonable, what I showed you before, 5/2. Okay, here are the 5/2, okay, which took a few growths to get it without this superlattice doping. You don't have all these many states that people usually see in the first excited Landau level, okay. But we see the 7/3, 1 and 1/3, the 5/2. The plateau is not very wide. It's about 300 to 400 angstrom only, okay. And the gap here is possibly about 0.2 to 0.3 Kelvin, okay? Not too bad at all. The 8/3 usually doesn't go somehow for whatever reason to 0, okay? And these are now on the other side, the 2 and the 3 filling factors. And I'm going to measure now all of them, okay, just to see, okay? So what do you expect the thermal conductance of 7/3? Number. How much? How many channels are here? Come on, guys. 7/3 is 2 plus 1/3. 3 channels, right? Thermal conductor 3. What am I supposed to measure at 8/3? Two, always 2. 8/3 and 2 plus 2/3. And the 2/3 is close to 0, right? So I'm supposed to measure 2 plus. The fact that you don't, or you are shy, or you didn't understand anything I said until now. Is it okay? Is it normal? 7/3 to be 3, 8/3 to be 2? Yeah? Okay. So this is expected to be 2. This is expected to be 3. And this one, I don't know what it's expected to be. Okay? Okay? Depends on order. Okay. So I'll go on now, and indeed, I don't want to elaborate now. Maybe I'll show you a couple of things, just that we do expect to get this, okay? And indeed we measure, and the 8/3, we need huge long equilibration maybe, and then we have to go to 5/2, okay? So I just want to show you, okay, how do we start measuring it all to see that we're making, right? So this is the 2/5, and we go through a QPC, closing, let's say, 1 hour, and you go down and we measure 2 under the 2.5. Okay, I can measure it, go to filling factor 2 and measure, but I would like to be 2.5 and measure the 2.5 below. This, among many other measurements, but this is just an example. I can measure the 2, and I can measure here the 1 under, okay? Okay, and so the same thing is this particular one, I can go here, if I measure filling factor 2, I get kappa equal 2. You see, allow me to say that this is 2. If I measure 1, allow me to say that this is 1. Okay? And this is this 4 minus 2 over 2. Remember, I subtract, etc., just to make sure. Okay, and this is another example, 7/3 and 8/3, low temperature. Okay, also here, I subtract, and I measure here instead of 3, I measure 2.86. But if you think about it, there are 3 channels there. 2.86 divided by 3 is 0.95. It's not bad. Okay? And this 8/3 is not 2. It's 2.1, but we saw in 2/3 already that it doesn't equilibrate fully. Okay, and finally now, this is just another example. I think that I go now. This is now, I give you now here, this is 5/2. Okay, so what I show you initially, we know that this particular contact over all the other integer measurement, this is the beta. So we put into the equation beta, we don't subtract anything, and we plot it, okay? It's 4 arms, 3 arms, 2 arms. No subtraction, just plotting, okay? And you see, okay, right, you measure TM, of course, you measure this, and you see this agreement, and you make now an average between these two, okay, and you get 2.54. Okay, so we get here a thermal conductance, and then you can measure it by subtraction. And then beta is irrelevant, we dump it out. Okay, and we subtract, okay, the subtraction procedure, 4 minus 2 by 2, and then we get 2.49. Okay. So, and then we can change temperature. And then we measure it at 18, 15, 12. And you see that it has this tendency to climb up as you cool down. Okay? So the assumption we had to say, great, okay, we have to show all this data here because it very well could be that the equilibration length gets longer and longer, like we saw it in 2/3 when we warmed up. Equilibration length gets shorter and it gets longer. And now you don't have full equilibration of this 2.5 kappa state, which I'll remind you in a minute what it is. So we did really a lot of measurements, okay? We have thermal cycling, okay? We made 17 measurements, different temperature, different location of the plateau, etc. Okay. So if you put them together, all these dots here, okay, and I plot it on this scale to remind you again, this is the Paphian, this is the anti-Paphian, this is the pH Paphian. This is the particle Hall state order. And this pH Paphian is 1, 2, 3, 1, 2, half, and a Majorana back. Okay? So it could very well be that this increase here, lowering temperature, the equilibration length gets longer, and this is the reason it climbs up. But that's the data. I'm just an experimentalist, I show data. Okay. So this, the reason I'll mention just in the next transparency. Okay, so finally we measure these 3 and 2 plus and 2.5, okay? And I just want to remind you again the table, okay? So it seems to be that we are measuring this one. I have a caveat in my last transparency. I'll give a sentence or two about maybe it's not, okay? But the most important part, aside from the order itself, which is important mostly for theorists, that there is a half. And I'm told by every almost theory that I'm talked to that if your measurements are correct, this is a smoking gun for Majorana. Okay. Okay. So this is a non-abelian state. Okay. And what I want now to add is work that Steve is working on now. As a matter of fact, if I can say that he was our referee also on the paper, he was brave enough to admit on the paper that let's think about it, that the Majorana mode fails to equilibrate, which could be. The whole issue of equilibration is super important And what our group is doing now is trying to measure equilibration, temperature equilibration. Okay? How do you measure equilibration between modes? It's not so simple. Because if you don't equilibrate, then your measurements are irrelevant, basically. But the fact that you saw that we have this plateau, okay, sort of plateau of 2.5 over I would say long, but somewhere between 15 and 25 millikelvin, and then climbs up, it shows that the number that we measure is reasonable. Okay? So what Steve says is that if the Majorana fails to equilibrate, then what happens then you really add, rather than having n down minus n up, you have n down plus n up. So if you go back to the anti-Paphian, instead of 1.5, rather than that comes out by you have to reverse the half, then you add 1, then you get 2.5. And why Steve wants the anti-Paphian, and I'll give him a chance to speak his thing, because all, as far as I know, all numerics suggest that it's a Paphian or an anti-Paphian. An anti-Paphian preferable. And the pH Paphian, all numerics show that there's no gap. So I remember when we gave the first talk, initial result, it was in EP2DS in Penn State. And we show this, that we see 5 halves. We see 5 halves thermal conductance of a state of 5 halves. The theorists were very alarmed. Halperin came pretty white and said it cannot be. Okay, so we went back home for another half a year to measure. Okay, so the point is now that it could be. It could be. We can argue about the details or so, but it could be anti-Paphian. I'll be as glad to prove that it's anti-Paphian. So Steve, do you have anything to add? Okay. So I think that's what I wanted to say, and I'll finish at this point. Thank you very much.
That's beautiful. I have a question about states like, let's say, the 2/3 state. And then it seems that if you have this equilibration, you're getting like an infinite Lorentz ratio because it still has charge conductance of 2/3, right? The thermal conductance is 0.
Uh-huh.
So it's like a superconductor in that respect. So because of that, is there any chance, experimentally, if you forget about theory, is there any chance that say 0.16 leftover thermal conductance you got is actually real, is actually the asymptote at long distance, or are you pretty confident that it would move down and go to 0?
No, I'm not confident. It could.
Because
but you see that
nice number, 1/6.
No, but, well, don't take it with a grain of salt. But you know that I raise the temperature, it comes down. Okay, so I'm not sure if I raise it even more. The point is that if you raise it too much, the state goes bad, okay, and you start getting other stuff. I can tell you what I measure only. Okay.
Because it'd be interesting if it's real.
I never thought about it. I thought we are approaching 0 very slowly. Look, we do now also another experiment that we look on upstream noise. Okay, just the noise going upstream, neutral mode going upstream, no thermal conductors, no nothing. And we look at the neutral mode going upstream as a function of distance. So we go all the way to 300 microns. And we see now that the noise, which suggests the energy going up, is decaying basically to 0. But if you go now to 3/5, it goes very fast down, but one mode remains, topological, and it stays constant.
Yeah, it's interesting. You're somehow cooling, if the charge mode is like a wire, you're cooling that wire in a way that it still carries current. Which is
Yes, yes.
Good. Other, no?
I didn't hear you. Can you speak up, please? Well, of course. I think I told you before, because I don't know how to interfere quasi-particles, I'm doing this. I think that there is work by Willett that does interference in 5/2, quite a bit of work in the last few years. I don't think that he sees what he claims to see different orders, but he claims to see non-abelian, okay? I am not very happy with this work, but in general, what you say, you have to braid particles, right? You have to braid them, okay? But I don't know how to do it yet.
I think that experiment, even if you believe what he claims about it, it doesn't distinguish between Paphian and anti-Paphian, and I'm not sure about pH Paphian.
I see. Okay.
I think you get the same result.
Okay. It goes from half, sometimes to half, sometimes to a quarter, you know, that you measure the H over, H over.
I think the same,
Yeah,
you would
yeah.
expect the same period.
Okay.
All right, any further questions? Let's thank the speaker again.
Okay.